Okay, so moving on to the next unit here, topic 2.8, tonicity and osmoregulation. Osmoregulation is just kind of this the the way that cells or organisms rather like to maintain certain levels of water outside of their cells and certain levels of water inside of their cells. So let's go ahead and take a look. These are some words you probably have seen before in class or otherwise. This is a cell right here, this yellow part, this orange part. This is the cell. This light blue part is, as you might guess, water. Um, this is a hypotonic solution. A lot of you remember this, thinking of hypo, meaning a cell in a hypotonic solution will expand. It will turn into fat. It will become a hippo, right? So, if you'll notice, there's a very low concentration outside. There's a high concentration of solute particles inside. This means that water is going to want to move in, kind of dilute this concentration of particles inside. An isotonic solution has an equal amount of particles on both sides, which means that you're going to have equal water movement both ways. That's isotonic. And then hypertonic, you might remember because hyper, a lot of these molecules, if you have a hypertonic solution, there's a lot of molecules out here, so they're very hyper. If you look inside the cell here, this orange part and yellow part, there's a lower concentration of solute, higher concentration out here. So you're going to notice that water is going to want to move out of this cell, and the cell is going to shrink, right, or shrivel. These are three words you need to know: hypo, iso, and hypertonic. Another way to look at it, if you want to look at it a different way, is look at this. Look how much blue you have out here outside of the cell. A lot of blue. That's water. You can think of that as being the water molecules. You got a hypertonic solution. There's less blue here, right? Water also moves from high concentration to low concentration. So a high concentration of water is going to move towards a lower concentration of water. So if you want to look at it either of those ways, you should be fine. I have another picture down here of an isotonic solution. These are blood cells. This is kind of a classic image of an animal cell. And what happens in a hypotonic solution? Well, as water flows into an animal cell, we don't have some of those nice features that plant cells have, like cell walls, to protect our cell. As water flows in, it will eventually lyse and, or break apart. It will become too full. It will pop like a balloon because too much water is flowing in. In a hypertonic solution, it will shrivel up. If you look at the similar thing for a plant cell, you'll notice that a plant cell will become an isotonic solution. Is considered flaccid. Water is moving in and out equally. A turgid cell is one in which it is expanded and it is filled with water. Of course, plants can handle an excess of water much better than animal cells can, which makes sense because they need water very desperately to photosynthesize. Hypertonic solution, you're going to notice the cell shrinks up inside of the cell wall. You can see these junction points where it's still connected. But the cell itself and that membrane is shrinking up inside here. This is a plasmolyzed cell. So, iso, hypo, and hypertonic. This describes the solution. These right. It's very important for osmoregulation. We can take a look at some osmoregulation in a couple of types of fish. If you want a nice example of this, if you think of a marine fish, what does a marine fish have? And I'll draw. I know I've drawn this in class a few times. And it's a fish, right? Instead of a cell. You have a high concentration out here, right? High concentration of salt outside of the fish in this situation. Other situation, of course, not living in this environment that we've been putting these plant cells in, this beaker environment, you have a lower concentration of salt outside in a freshwater fish, right? Salt water, very salty, high concentration of salt. Freshwater, you have a low concentration outside. So how does the fish deal with this? Well, water is going to automatically, osmotically leave these saltwater fish because it has a very salty exterior. So this high concentration outside, this water is going to naturally move outside via the gills. Also, some salt ions will move outside as well. In the freshwater fish, you're going to have an uptake of salt ions by the gills and osmotic gain through the gills because the fish itself inside is saltier than the environment, right? So this is kind of osmoregulation. These fish need to be able to maintain water levels inside of their cells, and the way they do that is by excreting and intaking kind of the right balance of things. You'll notice the urine in this freshwater fish is dilute. There's a lot of water moving out in this scenario, and that would make sense to you. Also, in the marine fish, you have a more concentrated salt urine moving out of this fish. So this is just one of the ways these types of fish regulate their salt levels. So let's go ahead and take a look at our plant cell. You've seen this before. We've seen it in class. This is a plant cell of some sort, submerged in some form of liquid, and we're going to kind of do a calculation here to kind of see what we're talking about. I'm going to write a few things inside the cell. We know, if you'll remember, that the total water potential of something is equal to the pressure potential plus the solute potential. So this is true inside the cell. Outside, also, total water potential is equal to the solute potential plus the pressure potential. Same formula here. Only difference is if water leaves the cell and enters this beaker, it's open to the air, right? It's open to the air right here, which means that there's not going to be a pressure buildup, so there is no real pressure potential. So if you find the solute potential, you have also found the total water potential. Okay, so I'm going to kind of move these formulas so that I have some room here to work. Also remember, there is one formula we need to know how to calculate, that is this one right here. Solute potential formula is negative I CRT, where I is the ionization constant, C is the molar concentration, R is the pressure constant, and T is the temperature in Kelvin. So you guys might want to make sure you have this in your notes or something, because I'm going to get rid of it again as we work through these. Okay. So what I typically do in these situations, if I'm given a question, first of all, don't always expect something to be drawn. These could be word problems, and I always recommend you actually draw this. Always draw this. I'm going to look at the caps up here. Always draw a model of this. It's worth the time. Absolutely worth the time to draw this and make sure you know what's going on. Even I do this. This is perfectly normal. What I like to do personally, this is just how my brain operates, but I draw a little chart up here. I know this is not the most straight lines, but I'll typically label it inside and outside. When I say inside and outside, I'm speaking of inside and outside the cell. Now, I'm going to operate here at, let's see, 27 degrees Celsius. We'll say we're at 27 degrees Celsius. And let's say we have a 2 molar sucrose solution out here. And inside we have a 4 molar sucrose solution. So first off, pause the video and I want you to tell me, is this solution hypotonic, isotonic, or hypertonic? Okay, you should have said the solution is, and I'll write it down here, hypotonic, right? Because there is a higher concentration inside than there is outside, meaning that water is going to want to move. Throw a little arrow here. Water is going to want to move in, right? Water is going to be moving in this situation. The cell will be getting bigger. Let's assume it's a plant cell and it's not going to explode. This thing is just going to get really nice and fat and turgid. Okay, so water's moving in. Let's go ahead and I'm going to write down all my variables that I can possibly solve in here. Total water potential. This describes where water is in actuality moving. The solute potential describes where the water wants to move based on what is dissolved in it, in this case sucrose. And the pressure potential equals the amount of pressure that is opposing the solute potential. The amount of pressure that's building up on the cell wall of these plants. Outside, we have a total water potential, and we have a solute potential as well. Of course, we have, again, no pressure potential because there's no pressure that can be built up in an open container. Okay, so the first thing you should be able to tell right now is, let me draw this line a little bit shorter, maybe a little bit better there. There we go. Side outside. So we have some solute potentials that we could calculate, right? 2 molar sucrose, 4 molar sucrose. Again, that's moles per liter. That's a measure of concentration. So we know that solute potential is equal to negative I, capital C, R, T. Okay, so let's go ahead and take a look at this. I, of course, is the ionization constant. For sucrose, or probably unless it otherwise says, the ionization constant is going to equal 1. And the only case in which the ionization constant is going to equal 2 is if it's some sort of salt, right? Cl2, if any Cl or some sort of salt. That's the only time this ionization constant is going to change. For us right now, it is 1 C. Let's calculate what do you guys want to do. Let's do outside first. So C is equal to 2 molar sucrose. 2 molar sucrose. Okay, R. R is going to be our pressure constant, which is always going to be 0.0831 liter bars. Liter bars per mole Kelvin. And T is going to be temperature. This is going to be temperature in Kelvin. So it's going to be 27 degrees Celsius. This is 27 degrees Celsius plus 273. You calculate Kelvin by taking your Celsius temperature and adding this number. So 1 times 2 times 0.0831 times 300 is going to give us our outside solute potential. So go ahead and pause, calculate that. I'll do the same, and then we'll come back and see what you got. So this solute potential you should have gotten for this is negative 49.6. And now that we've solved the solute potential outside, I think we can also safely say that the solute potential, or the total water potential outside, rather, is negative 49.6. So 2 molar sucrose, I'll put the water potential down here, or and the solute potential. Here is equal to negative 49.86 bars. That's the solute potential out here, which of course, keep in mind, is equal to the total water. Oops. It's also equal to the total water potential. Okay, let's go ahead and pause the video, do the same for this side over here. Keeping in mind the only change we're going to make really is sorry, got some technical difficulties there. The only change we're really going to make right here is changing this concentration here to 4 molar sucrose, right? So you're going to basically be saying for the inside, outside over here, I'll block this off. The outside, calculate the solute potential inside here. Solute potential is equal to negative, again, 1 sucrose. I'm not going to put the units in just to save us a little bit of trouble here and room. 4 molar sucrose, right? That's the concentration. R 0.0831 times 300. Obviously operating at the same temperature. Go ahead and calculate this out. I'll pause and do the same, and then we'll see what you got. Okay, you should have, or at least this is what I got, is the solute potential inside is negative 99.72 bars, right? Bars up here. Units on here. 72 bars. So, solute potential inside is equal to negative 99.72 bars. Now, you'll notice we did say water is going to move in based on the concentrations, 2 molar outside, 4 molar inside. We know water is going to want to move in. Let's look at it from the water potential perspective. Outside, your water potential is negative 49.86. Inside, it is negative 99.72. Water always moves towards the most negative water potential, right? So the lowest number here. So negative 99.72 is much more negative than negative 49.86. In fact, pure water, the highest this number is going to get is 0. Pure water has a solute potential of 0 because nothing is dissolved in it, right? So water's been moving in this cell. Let's say we've let it sit for a while. And what begins to happen is pressure begins to build up, right? As this pressure kind of builds up along the cell wall over here, right? That water is not going to want to move in because there's just too much pressure in there, so water can't move in as effectively. You tend to reach this equilibrium at a certain point where water is going to be moving in the same quantity as it's moving out. However, this is a little bit different than being in an isotonic situation because in this case, our cell is filled with water, right? And the water does indeed want to move in. It just can't because of this competing pressure potential. But since water is moving in and out at exactly the same rate, we can generally say that our outside total water potential, this number right here, is going to equal our inside water potential, which is this number over here. So if those two are equal, that means you've got negative 49.86 bars. Total water potential inside. Your solute potential is this, and if you have both of those numbers and you remember this formula over here, you can calculate what that pressure is that this cell is operating at. So let's go ahead and do that. We're trying to solve for the pressure potential inside. So if you look at this formula and you subtract the solute potential from both sides, you'll notice that total water potential minus the solute potential is going to give us our pressure potential. So let's go ahead and plug that in. Our total water potential is negative 49.86 minus negative 99.72 is going to give us our pressure potential. So go ahead and add this up and tell me what you got. Go ahead and pause it, and I'll do the same, and we'll meet up and see what you guys got. Okay, you should have gotten positive 49.86 bars as a pressure potential. So this is kind of a very basic, water potential problem. I hope this helps you understand the basics of water potential. Keep in mind, if the situation was reversed and you had 4 moles on the outside, 2 moles on the inside, your net movement of water would be outside. And then you get a lot of variables, so it becomes different to just calculate that pressure so easily. Know hypertonic, hypotonic, and isotonic. Understand how water potential works. Be able to calculate pressure potential. And we'll do a little bit more practice with some more complex problems in class, but this is kind of the basics of it right here. And if you have questions, come see me. Thank you for listening.